Hello, everybody. This is the second week, and we start a new chapter, a slightly more abstract aspect of linear algebra. What is the title? Vector subspaces of Rn, linear dependence, and linear span. Remember that vectors in Rn are always column vectors. That is, they are n cross 1 matrices. So what is a vector subspace of Rn? A subset V of Rn is called a vector subspace if first of all it should be non-empty. And if whenever pick a vector in V and a scalar A, the product A times X must be in V. We can take a vector and we can multiply a vector by a real number, right? You can take a matrix and you can multiply a matrix by a real number. You simply multiply all the entries of the matrix by that real number. So take a vector X, let its components be x1, x2, x3, dot, 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 xn. That's a column wise. And you picked such a vector from V. And A times X must also be in V. That is, after A x1, A x2, dot, 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 A xn. And whenever I pick up two vectors from V, the sum must be in V. In mathematics, we say V is closed under vector addition and multiplication of vectors by scalars. Let's look at a simple example. Let us take the subset V to be in R3. So what subset am I taking? All those columns x, y, z in R3 such that x plus y minus 3z equal to 0. I had taken a specifically and deliberately an easy example so that your visualization is easy. You can visualize this as a plane in R3 passing through the origin. We want to prove that this subset V is a vector subspace. Obviously, this is a non-empty set because 0, 0, 0 is certainly in V. It's non-empty. Okay, so now let us pick an element x, y, z in V and let us pick a scalar A. What does it mean to say that x, y, z is in V? It means x plus y minus 3z equal to 0. Multiply this by A. You get ax plus ay minus 3 times az is 0, which means ax, ay, az. The column vector ax, ay, az is again in V. In other words, if an element is in V, and if I pick a scalar A, multiply the scalar times this vector, and it's again in V. V is closed under multiplication of vectors with scalars. Next, I must check that V is closed under vector addition. I pick up two vectors, x1, y1, z1, and x2, y2, z2 in V. What does it mean to say that these are in V? It means x1 plus y1 minus 3z1 is 0. And x2 plus y2 minus 3z2 is 0. That is, these 2 points lie on that plane x plus y minus 3z equal to 0. So add these two equations, you get x1 plus x2 plus y1 plus y2 minus 3 times z1 plus z2 is 0. That means that the sum of the two vectors x1, y1, z1 and x2, y2, z2 is again in V. V is closed under addition. So these three requirements are satisfied, non-empty. Multiplying a vector by a scalar, pick a vector from V and pick a scalar, the product ax must again be in V. Pick two vectors in V and the sum must again be in V. So this is being satisfied by in this example. So here is an example of a vector subspace of R3. The next example is an example which is not a vector subspace. Explain why V equal to x, y, z column vector in R3 such that x plus y minus 3z equal to 1. That is not a vector subspace of R3. Why is it not a vector subspace of R3? Of course, it's non-empty. No doubt it's non-empty. But let us take an element here. I could take an element 1, 0, 0, right? Is 1, 0, 0 in V? Of course it's in V. It satisfies the equation x plus y minus 3z equal to 1. Take an element A, take a scalar A. I choose the scalar A to be 0. 0 is a real number and I choose my A to be 0. And check if I multiply A with x, y, z. If I multiply A with x, y, z, yeah, there is a small point here. Unfortunately, I used x, y, z and I used x as an element of V. I should make it bold-faced. Unfortunately, while I'm writing, it's not getting bold-faced. This x here should be bold-faced, okay? just think of this x here, x as a boldface. When I'm sending, I'll send out a correction. I will share these sheets with you. In this sheet, I'll try to make it boldface. This x here must be a boldface, and this x here must be a boldface. Okay. So I pick an element from V, and I take a scalar A, which is 0, and the product is going to be 0. Is a 0 vector in V? No. 0 plus 0 minus 3 times 0 is not equal to 1. So this is not closed under multiplication by scalars. So this is not a vector subspace. Next is an exercise. Show that a line passing through the origin in R3 is a vector subspace. What is the line passing through the origin? Can you describe a line passing through the origin in R3? You think of it, and you write down the line passing through the origin as a set of points, and you show that that set is closed under vector addition and multiplication by scalars. A plane passing through R3 is a vector subspace. You would have probably guessed there is nothing sacred about this 1, 1, and minus 3. I could have taken any other plane. I could have taken 5x plus y minus 3z equal to 0. I could have taken 7x minus 2y plus 3z equal to 0. I could have taken any plane. I can change these numbers. I can change this coefficient. I can take alpha x plus beta y plus gamma z equal to 0. And you would have guessed that. So a plane passing through the origin in R3 is a vector subspace. R3 itself is a vector subspace. So my V is the whole of R3. Of course, if my V is the whole of R3, and if I take two elements in V, if I take two elements in R3, the sum is in R3. R3 is non-empty. And if I take a vector in R3 and multiply it by a scalar, again it's in R3. So R3 itself, trivially, R3 is a vector subspace of R3. That's a trivial example. The plane is a non-trivial example. A plane passing through the origin. A plane passing through origin. Again, the word origin is missing here. A plane passing through origin in R3 is a vector subspace. I will make these corrections and I will send out before sending it out to you. R3 itself is a vector space of R3. The singleton, consisting of only the 0 vector, is a vector subspace of R3. Here again, I repeat, a plane passing through origin in R3 is a vector subspace. Plane passing through origin in R3. So the origin in R3, that word is missing. 0 belong to R3. That is missing. I will send out when I share these sheets with you. I will send out the correction. Thank you. The singleton, consisting of the 0 vector alone, is a vector subspace of R3. So what are examples in R3? Line passing through the origin, plane passing through the origin. If a plane doesn't pass through the origin, it is not a vector subspace. No, this plane doesn't pass through the origin. X plus y minus 3z equal. So it's very important to make this correction. A plane passing through the origin in R3 is a vector subspace. Then the singleton, and there are two trivial examples. R3 itself is a vector subspace of R3. The singleton is a vector subspace of R3. Question: are there any others? Can you justify it? Are there any others? Okay, suppose if V is a vector subspace of R3. Suppose V is a vector subspace of R3. V is of course non-empty. It must contain a vector. It may contain only the origin, in which case we are in situation 4. Or it could have a non-zero vector. Let us pick a non-zero vector U. Let us pick a non-zero vector U. And the moment a non-zero vector is there, any multiple will also be there. It must be closed under multiplication by scalars. So the moment I pick a non-zero vector and I multiply it by a scalar, again the product should again be in V. So once I pick a non-zero vector U and start scaling it, multiplied with all possible scalars, what will you get? You will simply get the line through the origin. So if you're exhausted, so if you get the whole of V, and if it exhausts your V, then we are in situation 1. Or it doesn't exhaust V, right? So you're taken this line, and there's a point V, there's a point, another point W, which is outside the line. Then you've got V. So you got U and W. So U and W are there in your bag, And so and so you must be able to multiply. I can multiply u by a scalar au, that must again be in V. I had taken a w in V and I multiplied by another scalar b. So au plus bw, au plus bw must also be in V. And so, but if I start taking all possible, if I start taking all possible scalars a and b, and I look at au plus bw, think of the parallelogram law of vector addition. U plus W, 2U plus W, U plus 2W, AU plus BW. Think of plot all these points. What are you going to get? You're going to get a plane through the origin. And we'll be in situation number 2. To the plane, so if this plane is the whole of V, then we are in situation number 2. Otherwise, that means that there is still yet another vector which is outside. And then I will call that third, that Z, for example. So you got AU plus BW plus CZ. And I will start varying AB. I will start varying ABC, but then I'm going to get the whole of R3. So I'll be in situation number 3. So what is the answer to this question? There are none others. These are the 4 examples of vector subspaces of R3. Lines through the origin, planes through the origin, the whole of R3, and the singleton set consisting of 0 vector alone. So now that is a nice geometrical example. Now let us do a little more algebra. Suppose you have taken vectors v1, v2, vk in Rn. You have taken vectors v1, v2, vk in Rn, and I take scalars a1, a2, ak. Then I form a1, v1 plus a2, v2 plus ... plus ak, vk. This combination a1, v1 plus a2, v2 plus ... plus ak, vk is called a linear combination. It's called a linear combination of v1, v2, vk with coefficients a1, a2, ak. Now let us consider the set of all possible linear combinations. You have taken a fixed bunch of vectors v1, v2, vk, and I'm going to take all possible scalars a1, a2, ak, and I'm going to form all possible linear combinations a1, v1 plus a2, v2 plus ... plus ak, vk. And I get a basket of vectors. I get a whole bunch of vectors. I get an aggregate of vectors. Call this aggregate V. Check that V is a vector subspace of Rn. Check that V is a vector subspace of Rn. It is non-empty because if I take A1 to be 0, A2 to be 0, AK to be 0, then I get 0 V1 plus 0 V2 plus 0 VK. That linear combination is 0. So V contains the origin. V contains the 0 vector. So it's non-empty. Now if I take A1 V1 plus A2 V2 plus AK VK and multiply it by A, I'll get A1 V1 plus A2 V2 plus AAK VK. That's again a linear combination of V1 V2 VK. So again it is in V. So V is closed under multiplication by scalars. Now you check that V is also closed under vector addition. If I take 2 elements of V, the sum will also be in V. So check that V is a vector subspace of Rn. This particular vector subspace V is called the linear span of V1, V2, Vk. This is called the linear span of V1, V2, Vk. Given a bunch of vectors V1, V2, Vk, what's the linear span? Simply take all possible linear combinations. Take all possible scalars A1, A2, Ak, and then you form the combination A1, V1 plus A2, V2 plus AK, Vk, and the aggregate of all these things that you get is the linear span. Question. Suppose V is a vector subspace of Rn. Can you find a finite subset S of V such that V is exactly the linear span of S? See, what we did earlier is we took a finite set of vectors and we formed the linear span and we got a vector subspace. The converse question I'm asking, suppose if I take a vector subspace of Rn, can you find a finite subset S such that if I take the linear span of S, I get my V? We shall answer this question very soon. Now let us go back to star. We say that V is generated. We also say that V is a linear span of V1, V2, Vk Another way to say this, which is common in mathematics, is V is generated by V1, V2, Vk. Both these terminologies are being used. V is the linear span of V1, V2, Vk. Is exactly the same as saying V is generated by V1, V2, Vk. If you read different books, they will use these phrases interchangeably. They mean the same thing. All right. So let us go back to our example of garden variety. X plus y minus 3z equal to 0. Okay, or V is a set of all column vectors x, y, z such that x plus y minus 3z equal to 0. That's a more precise way of saying it. So I picked up two elements in V, 3, 0, 1 and 0, 3, 1. They both lie in V. It's obvious that they both lie in V. Now prove that the linear span of these two vectors is precisely V. So this question that I raised, if I give you a vector subspace, can you find a finite subset S such that V is exactly the linear span of it? This question we're answering yes in this example. So we are looking at this question in the light of this example. Okay. So 3, 0, 1 and 0, 3, 1. Now please tell me, is 3, 0, 1 and 0, 3, 1, are they collinear? They are not collinear things. The vector, the arrow starting from 0, the position vector of 3, 0, 1 and 0, 3, 1, they are not collinear. The second one is not a multiple of the first one. 0, 3, 1 is not a multiple of the first one, nor is the first a multiple of the second. These two vectors are not collinear. So now what will happen if I take the sum of these two vectors? If I take the sum of these two vectors, I'm going to get the parallelogram. 0, 0, 0, 3, 0, 1, 0, 3, 1, and the fourth point is the sum of these two. Now what you do is that you start multiplying the 3, 0, 1 with A and 0, 3, 1 with B, where A and B are real numbers. First you start with positive real numbers, and then you start forming the sums. So you do A times 3, 0, 1 and B times 0, 3, 1 and add them up. You will get points in the plane. Question is that by varying your A and B, are you going to cover the whole plane? That's a geometrical, think geometrically and answer this question. Answer is yes. The plane V, this V is going to be exactly the linear span of 3, 0, 1 and 0, 3, 1. Namely, if you take all possible linear combinations of these two vectors, you're going to get the whole plane. Now the next question is that, so I have given you a subset consisting of two elements whose linear span is V. You might ask, can V be generated, or V is generated? In other words, V is generated by V1 and V2. So we got a generating set. We got a set consisting of two elements whose linear span is V. Can you do better? Can you get a set with one element? Can you find a subset of V with simply one element such that the linear span is the whole of V? What will happen if I just take one single element and try to take its linear span? I'm going to get a line. I'm not going to get the plane. So one single element will not be able to generate my V. Or we could try to look at a larger set. You can have a 3 element set. What about finding a set with 3 elements which generates V? Of course, suppose for example I take V1, V2. I take a set consisting of V1, V2 and V1 plus V2, 3 elements. And if I start forming the linear and call V1 plus V2 as V3, call V1 plus V2 as V3 and start forming linear combinations. AV1 plus BV2 plus CV3. That is AV1 plus BV2 plus C times V1 plus V2. But you will say that is redundant because this combination can be written as, you can simplify it, no? You can write it as A plus C times V1 plus B plus C times V2. So call A plus C as alpha and call B plus C as beta. So basically you're looking at alpha V1 plus beta V2. So we are not done any better. Whatever you could get by taking linear combinations of V1, V2, and V3, you could get the same thing by just taking V1 and V2, because the scalars, your alpha and beta, will vary over all real numbers. So taking 3 elements of V to generate V is a little redundant. So you'll now begin to see that this 2-element business, this V, which is a linear span of V1 and V2, having a 2-element generating set is kind of optimal. It is an optimal situation. Fewer than 2 elements, you will not be able to cover the whole of V. Taking more than 2 elements in V may be a little redundant. So now you might begin to suspect that maybe this optimal number of elements 2 has something to do with the fact that the plane is geometrically a 2-dimensional business. You're right. If you're thinking so, you're thinking correctly. The dimension of this vector space is 2, so you can get a generating set with exactly 2 elements. You cannot, if the dimension is 2, you cannot get a generating set with 1 element. You can get a generating set with more than 2 elements, but that is redundant and perhaps wasteful. And so this optimal number is exactly 2, and this 2 is somehow the dimension. So the idea of doing this geometrical example is that I want to motivate the idea of dimension. We want to precisely define the intuitive notion of dimension. Okay. All right. Dimension is the most fundamental idea in mathematics, and we are converging towards a rigorous and precise notion of dimension. Before defining dimension, before attempting to define dimension, we need one more basic concept. And what is that new concept that we need? We need the concept of linear dependence and linear independence. Let us define this notion of linear dependence and linear independence. So from your basic geometry, look at the notion of collinearity in R3. Suppose I take 2 vectors V1 and V2 in R3. We say that V1 and V2 are collinear if one of them is a multiple of the other. If one of, say, is V2 is lambda V1, for example, I could rename the vectors. One of them is a multiple of the other, but so I could call one of them V2 and other one V1, and V2 is lambda times V1, or V1 is mu times V2, whichever way we want to think about. Or I can write this equation V2 equal to lambda V1 as lambda V1 plus minus 1 times V2 equal to 0. Okay, so now this equation has the form A1V. So this above equation lambda V1 plus minus 1 times V2 equal to 0 can be recast as A1 V1 plus A2 V2 equal to 0, where the second coefficient A2 is not 0. I do not know whether lambda is 0 or lambda is not 0. I don't have that information, but definitely one of the coefficients is not 0. That is, so you show that vectors V1 V2 in R3 are collinear if and only if there exists scalars A1, A2, not both 0, at least one of them non-zero, such that A1, V1 plus A2, V2 is 0. Okay, this is a more symmetrical formulation than the earlier one. The earlier one is an unsymmetrical formulation. There's a minus 1 sitting somewhere and there's a lambda sitting somewhere. This one is more symmetrical. A1, V1 plus A2, V2 is 0. At least one of them is non-zero. So what about vectors V1, V2, V3 in R3? V1, V2, V3 in R3 are said to be coplanar if one of them lies in the plane spanned by the other two, right? The plane spanned by the other two. So V3 is a lambda V1 plus mu V2. Okay, that is right. So I can write this as lambda V1 plus mu V2 plus minus 1 times V3 is 0. And one of the coefficients, so I can write it as AV1 plus BV2 plus CV3 is 0, where at least one of ABC is not 0. Okay, so you can say that prove that 3 vectors V1, V2, V3 are coplanar if and only if there exists scalars A1, A2, A3, not all 0, such that A1, V1 plus A2, V2 plus A3, V3 is 0. So that is a more symmetrical formulation of coplanarity. So collinearity and coplanarity, linear dependence is a generalization of these two ideas of collinearity and coplanar. Vectors v1, v2, vk in Rn are said to be linearly dependent. They are said to be linearly dependent if there exists scalars a1, a2, ak. If there exists scalars a1, a2, ak, not all zero, at least one of them should be non-zero, such that a1, v1 plus a2, v2 plus dot, dot, dot plus ak, vk must be zero. If v1, v2, vk are not linearly dependent, we say they are linearly independent. So what does it mean to say? Let us define linear independence. We say that v1, v2, vk are linearly independent if for scalars a1, a2, ak, whenever a1, v1 plus a2, v2 plus ak, vk is 0, the only way you can get 0 out of these vectors is taking all the coefficients to be 0. It cannot happen that the linear combination is 0 with at least one of the coefficients being non-zero. If that happens, you'll say it's linearly dependent. Linear independence means the only way I can create 0 out of these vectors is to take all the coefficients to be 0. That is a1, v1 plus a2, v2 plus dot, dot, dot plus ak, vk equal to 0 implies a1 equal to 0, a2 equal to 0, dot, 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 ak equal to 0. Convention, very important convention. An empty set is considered to be linearly independent. Empty set is considered to be linearly independent. If a set contains the 0 vectors, it is linearly dependent. Exercise. A set containing the 0 vector is linearly dependent. A subset of a linearly independent set is again linearly independent. Subset of a linearly independent set is again linearly independent. Now, they are going to prove the first fundamental lemma in linear algebra. This is one of the most important and the most foundational result in linear algebra. Everything that we do will depend upon this. Before you study the statement of this theorem and the proof of this theorem, you must go back and revise linear independence, linear dependence, linear combinations properly, because everything will depend upon these concepts. The notion of linear independence and linear dependence is one of the most important and most fundamental ideas in linear algebra, and you must understand the definition very precisely, very correctly, and then you plunge in to this proof of the fundamental lemma in linear algebra. What is the fundamental lemma in linear algebra? Suppose V is a vector subspace of Rn. Suppose V is a vector subspace of Rn, and suppose you know that V is generated by k vectors. That is, you know that there are k vectors v1, v2, vk sitting inside V, such that if you take linear combination, such that the linear span of v1, v2, vk is V. In other words, if you take all possible linear combinations a1, v1 plus a2, v2 plus ak, vk, where the a1, a2, ak vary over all possible real numbers, you get your whole of V. So V is a vector subspace of Rn generated by k vectors. Okay, and if you pick up k plus 1 or more vectors, if you take k plus 1 or more vectors in V, then they will be linearly dependent. They will be linearly dependent. As an illustration, let us take R2. Let us take R2. R2 is a vector space. R2 is a vector subspace of R2. What it is generated by 1, 0 and 0, 1. 1, 0 and 0, 1 generate R2. So R2 is a vector space generated by 2 vectors. So if I take 3 vectors in R2, they will be linearly dependent. One of them can be written as a linear combination of the other 2. They are coplanar. They are already coplanar because you know that the 3 vectors are sitting in the same plane. It's R2. So that's an illustration. R3 is generated by how many vectors? 3 vectors. 1, 0, 0, 0, 1, 0, 0, 0, 1. So I have 3. I have a generating set containing 3 vectors. If I take 4 vectors in R3, they will be linearly dependent. There will be 4 vectors in R3 will be linearly dependent. Okay. The proof will be by induction on K, and we will take it up in the next capsule of half an hour, and this completes the lecture 4A. This completes lecture 4A. We'll continue